All right, so yeah, I'm going to do the presentation from the Civil Conference, and basically what we're going to be looking at is utilizing GC, generative components, within your Open Civil environment. All right, so here's a quick agenda of what we're going to kind of go over. We're going to do a little bit of a brief introduction of what GC is, some background with it. We'll cover the interface, and then we'll talk about the workflows. From that, we're going to jump into a couple use cases, and then we have a rough demo that we can walk through. We're not going to be bouncing back and forth in the presentation, but I'm going to kind of be talking through the steps to set something up. Then we'll jump into some more advanced topics of GC, such as generating your own custom nodes, as well as some GC script language. And then we'll take a look at some greatest hits or examples of what we use GC for, and then we'll open it up to questions. But just kind of put this out there, the goal of the presentation isn't to get everybody, intimately familiar with GC. Hopefully it's enough to get you exposed to what's there, and then the interface to give you enough knowledge to start experimenting with it. So that's the overall goal and takeaway of this, is just to kind of show you how to open it, how to get started, and start experimenting with making different things. All right, so what is Generative Components? Basically, Generative Components is Bentley's visual scripting add-in. It's been around for decades, I feel. It's just never really been integrated fully with the civil products. It does have a lot more integration within open buildings. There's a lot more capabilities with it. I haven't really explored all of them, but I just know it's more integrated with that. But just because it's not fully integrated doesn't mean we can't use it for building content. So some examples that we commonly see within the civil environment is used for more detailed retaining walls, sign structures, noise walls, rail ties, anything that can enhance some of the current modeling features within your OpenX platforms. So just to kind of hammer home the point, GC is not fully integrated within the civil products, and it doesn't take advantage of all the capabilities that the civil products themselves inherently have. But we can leverage GC into real workflows. There's an upstream workflow where we're going to consume or produce and then consume it. And then there's a downstream in which we populate data and then we use it within OpenRoads or the Open Civil products. So we're going to take a look at both workflows and how they kind of tie into each other. And then we'll look at a demo on how we can build some content. So putting this disclaimer out there, yes, it's not fully integrated. And then the future, which many of you probably saw, that there's now Python integration coming with MicroStation. And I would expect that this is going to be carried through into all of the OpenX products moving forward. So I can see GC kind of fading off and not being used, if not as much, if not used at all in the future. But I still think in the immediate to medium term, there's still a use for GC, and it can still provide value. But as we see that Python integration coming in, there's probably going to be less need for it, and Python should be able to handle a lot more than what GC can do right now. So why are we using it? Basically, we see LOD requirements increasing and more models being the deliverable as a requirement from a lot of clients across the country. GC allows us to build more information and help facilitate that LOD need. Some model elements get looked over in current OpenX products. So we can use GC to create models for use directly or as a consumption workflow within the OpenX environment. So an example of that would be like a sign structure. We can generate a model within GC and then utilize that as a cell within a feature definition inside of the OpenX environment. And then another use is like the last mile authoring. There's many disciplines on infrastructure projects that maybe don't have a workflow within the OpenX environment now. And GC allows you to generate models and build content so that they can be leveraged within that OpenX environment and ultimately into an iTwin. So it just helps fill a gap where there might be missing pieces within your overall model. So where do we get it? Basically, GC is a free add-in that comes with all of the installation packages. Basically, just check the box and modify and install the product. All right, so let's take a look at the interface. So once you have it installed, there's going to be three major components to GC as far as the interface goes. You've got the graph, and the graph is basically where you're going to be placing all of your nodes and wiring them together to visually script the element that you want to build. It's basically the primary function is just to organize and relate all of the various nodes together so that it assembles whatever element you're trying to build. You're going to want to keep it organized, and these graphs can grow exponentially as you start to build more complex elements. So we'll touch on this a little bit later, but it's good to build pieces and then assemble things together through the use of like GCP extensions, the generative node types. We'll take a look at that in a little bit. But this gray area you see here, let me get the laser pointer. This area you see here is your graph, and that's where you're going to be taking your nodes and just dragging and dropping them on here. So next we'll talk about nodes. These are all the commands you can use to build elements. So think of this as, I want to create something, so I need to provide inputs into that something to facilitate it. They can be anything from polygons to points to coordinate systems. It's the arrangement of these nodes, and the arrangement of the nodes is how you're going to build the element you're trying to build. So for example, if it's a sign structure, you're going to be assembling all the various pieces of this and then using these nodes to do things like build circles and then extrude them and then subtract out smaller circles to get the object that you're trying to build. And we'll touch on that as we get into the demo. So that's the nodes over here. On the right-hand side is our transaction list. And transactions are basically the list of commands or nodes that you assemble in your graph as you save the file. And this is actually very helpful because it's a very good tool to help with iterations of your script. So it allows you to remove tasks or commands if something is maybe redundant, or if there's a better way to do it. You can easily go through and delete out specific nodes, or you can save these as like an archive version. So the task list itself gets saved external to the file as a GCT extension. And basically it's just, you can open it with a Word doc and it just lists all of the commands that are in there per transaction. And it's really helpful if, say, like your file crashes, you can just reload that GCT file and have your GC model back. So it's a very powerful and handy tool within GC. All right, so let's talk about the workflows and how we actually can use this. So we have two workflows. We have a downstream and an upstream. So the downstream is going to require having your model referenced into GC. So basically you're consuming something that's already been built, whether it's a roadway corridor, a piece of geometry, anything. You want to decorate an existing corridor that you've done. So you're going to reference that in. You're going to set up some range boxes to find specific elements, whether that be whether you're searching based off of a level or an object, but you can find this information from your model and then essentially trace it with GC geometry. And then once you have it in GC, that's where you can start to decorate and build with various tools and commands. So that's the downstream. The upstream is the production side of where you're going to be building a model, which will then be consumed in the OpenX environment through the use of 99% of the time a feature definition. So basically building a cell, adding it into a DGN lib, and then consuming that cell with a feature definition. And that, I think, is the preferred of the two workflows because it opens up the ability to add additional attribution or leverage some of the existing technology within the OpenX software. So having item types or being able to annotate better, things like that. It brings it into the native software and allows you to do more with it. All right, here's just a quick snapshot of how you would assign that within the element template. So A lot of this is going to be focused on the digital delivery workshop that we built some content for. We had a bunch of overhead sign structures in there, but ultimately what we did is we built these GC models that represented our overhead sign structures, and then we exported those out to a cell. And then we simply put that cell into the work set and then created a feature definition that pulled that cell through the element template. So we had a 2D and 3D version of it, very similar to like how you would build like a drainage and utilities cell. We had a plan view and then a 3D view for placing it. But this becomes very powerful if you use this workflow for downstream efforts. So if you're looking at data visualizations in an iTwin, it can really help with highlighting different pieces. All right, so let's look at the use case here. Again, overhead sign structures, it's a popular one. So for the conference, we built all the overhead sign structures within that area for that digital delivery workshop. All of the nodes that we used were out of the box, so we didn't really create anything custom per se. We used some of just the out of the box technology to build everything we needed. We exported that out to a cell, and then we used it with a point feature definition. For noise walls, that's another popular one that we've done. Basically, what we did is we set up some civil geometry within OpenRoads, and then we set up some range boxes to essentially find the symbology of that civil geometry. And then from that, we hooked up a spreadsheet to that GC geometry, and then placed a couple coordinate systems on to organize on the placement of the posts, and then use some custom scripting to do some panel placements on that. But we'll look at this a little bit later, but there's a node within GC that allows you to link to Excel. And then once you have that Excel sheet linked, you can essentially pull different columns and you can organize and have a spreadsheet basically run your GC model, which is pretty powerful. It comes in really handy for like linear repetitive things such as like tie placements, or for noise walls like the post spacing, or if you're doing like a cable barrier for posts on there as well. So a lot of like repeated linear objects, it becomes very powerful. So just mentioned rail ties is another good example. So the out-of-the-box tie placement within OpenRail, it's good and it gets you what you need. But if you need additional detail with those ties, it doesn't quite meet the LOD requirement that you may need. So what you can do is set up a GC model to essentially place a custom cell at an interval based off of the geometry that you have set. And that works the same with any like special track work feature. So like a turnout or a crossover, you can build a GC model to essentially hang on the geometry that's already been developed. Retaining wall components is another popular one. So thinking about retaining walls in OpenRoads, basically you're just getting a component object, like a 3D mesh that is generated from your template. So that isn't going to give you the panels or individual straps or things like that. So what GC allows you to do is essentially build any array of points or objects relative to the geometry developed from OpenRoads. So you would reference in your OpenRoads model with your top and bottom of wall, create a geometry relative to that, and then start placing objects so that you can turn off your component and turn on this GC model and have that kind of sit in its place. And it's really helpful for things like wall panels, so like a MSE cruciform or just like a rectangular panel. It's helpful for straps or geotextile areas, layers that you may have, T-walls, as well as soil nails. Soil nails is actually probably the one I'm diving into right now, but soil nails I think is going to have a really powerful visualization to it to understand things. All right, so let's look at a quick demo walkthrough of how we can kind of assemble something within GC. So looking at the CDOT cantilever sign structure, that's what we used. We use these standards to build the digital delivery workset. But overall, the approach is going to be something similar to identifying the workflow that you want to do. So is it going to be the upstream or the downstream? Do you want to build the content and consume in ORD, or do you want to build your model in ORD and then decorate it with GC? And for this, we did a upstream where we built the content first and then referenced it into the to the workspace for use in the point feature definition. So looking at this cantilever sign structure, we identified the workflow, and then we're going to identify the various pieces and then the variables associated with it. And then once we have basically an idea of how we would split this cantilever up into smaller pieces, then we go through and look at the graph and transactions and nodes and how we can start assembling those individual pieces and putting them together. So workflow identification, we're going to go with the upstream on this. So we're going to build a cell. And then understanding that, now we need to look at the standards themselves and see, all right, how can we split this up? So just looking at the pieces of this, we have a ton of them. So there's the arm span, there's the elbow, the column, the caisson, the U-bolt assemblies, the actual C-section holding up the sign itself. So there's a lot of smaller pieces that you can build, which are generally easier to build individually than to try to do this entire thing as one GC model. So generally my approach is to try to split these up into smaller pieces, build them as their own, and then reference them together as best I can as far as using GCPs, the generative node types. So we want to keep in mind the interaction of these elements and how they fit together. What are the variables that are driving them? And if you understand how this thing is designed and built, then you're essentially just recreating that methodology within GC by linking nodes together. So we've identified the pieces here. We're just going to look at a portion of this. We're going to be building the base plate just to keep it simple and get something created. All right, so looking at the cantilever itself, we have identified a few different components here that are all relative to common variables. So this is generally my experience with the sign structures. A lot of the agencies have very similar standards on how monotubes are built. They're a function of the diameter, and as the diameter is set based off of the sign area. So those are going to influence your span lengths, your heights, the diameter of the monotube. So it also influences your bolt spacings. So there's a lot of pieces that are dependent on your monotube diameter. So if we keep that in mind, what we can utilize in GC are some value nodes, which will make this more dynamic with the appropriate linkages together on this. So it's a lot easier to go through and modify, 2 or 3 different value nodes and have that cascade through than to go through all the various nodes and update the diameters if it's dependent on it going node by node. So it's always helpful to identify common variables within all of your components. That way you can pre-build those when you bring them together so that it's a quick linkage when you start assembling your overall model. All right, so here's where we're going to get into actually building it, and I'll show some screenshots here of how this stuff works. So we're going to assemble the graph now, now that we have an idea of how we want to build this. So we're going to look at the base plate, which is just a smaller element, but it covers a lot of the tools that it covers a lot of nodes that we're going to be using for basically every part of this sign structure. We're going to look at solid creations, solids by Boolean functions. We're going to look at the function node itself and how we can set up a series. And we're going to look at coordinate systems. So a lot of these nodes that I'm going to show, they're going to be used basically in any GC model. They're very common and they're used a lot and can be leveraged a lot. All right, so first step is to always establish your base coordinate system. GC needs to be a 3D DGN, and you need to have a point of reference for how all this information gets built. So you always have to start by establishing your base coordinate system. And then from this base coordinate system is where we can create additional coordinate systems to build objects away from the origin. So for example, the downstream GC workflow, this is where you would have an offset coordinate system that is relatively the negative XY value of your project coordinates. That way, when you reference your DGN in, you're linking it to that offset coordinate system so that the file comes in at the origin. GC doesn't like really big values for X and Y. It starts to get really wonky as you get further away from the origin. So what this does is it facilitates GC by bringing the model to your origin. And then from this, you can export it back out from the base coordinate system. So it puts it back in the proper location. Let's see, it's always, yeah, so if you're using that workflow, it's always the best practice to bring in your offset coordinate system relative to basically the center of your project location, depending on how big it is. If it's a small section and you're only building in a certain area, you can refine it down and have it more specific. But generally speaking, you want to take that rough XY of the middle of your project and use that as your negative values for your offset coordinate system. But here we see basically what we're doing is we're just clicking on our base coordinate system up here. And once we clicked on that button on the ribbon, it gave us this node called base ES. And that's what it does. It places the node here. Now, once we save that, we hit save, we're going to see that transaction get listed here. And again, what this is doing is recording all of these steps or nodes that we have done on our graph and saving it as a record here. And as we progress and start building more and more nodes, we can save and we'll see transactions populate here in our transaction list. All right, so taking a look at the base plate, if we look at the standards, we can see here that there's different iterations based off of whether it's a portal or a cantilever. And then from that, we have different flange stiffeners that we need to account for, different hole pattern, bolt patterns for it. And again, it's all dependent really on the monotube size. So ideally what we would have set up are a few different value nodes that would feed into all of these various nodes that are going to build our bolts, going to build the diameter, our base plate diameter, as well as the smaller holes that we're going to use to subtract them out. So it's always helpful to kind of pre-plan what you're going to be building. So if we know we're going to build the base plate, we want to try to identify all the variables that are going to influence this, and then try to use those as value nodes so that we aren't updating 100 nodes, we're only updating 10 per se. So with this, we're going to use the base CS and build everything relative to the base CS, because ultimately when we reference all this together, that's going to be our origin point for the cell itself. So we're just going to build it relative to our base CS. We don't have to worry about moving it anywhere. We're going to use some solid nodes to extrude a thickness, and then we're going to use value nodes for the input parameters relative to our pipe diameter, the radii, etc. All right, so here is where we have a graph with the value nodes feeding into the circle node. So what we did is we just clicked on our circle node over here, drug it over, and then in there we have different arguments that we need to satisfy in order to build that object. And we'll see that on the next slide here as I go. But basically what we need to do is identify a technique, so how the circle is going to be built. And then each technique is going to have different arguments that we need to satisfy. So let's see what that looks like. So right here, this is our circle node. We can see that circle, and the technique that we're going to do is by center and radius. And when we select that technique, these are the arguments that we need to satisfy in order to build that object. So we need to identify what the center point is, what the radius of that circle is, and then which support, which design plane are we working in. So for us, we're going to be working in, the center point is going to be our base CS. We're going to do it right at the origin. we're going to use the value node that we have in here, which is basically half our diameter for the radius. And then we're going to specify just the XY plane for our support. So looking at the nodes themselves, we can go through and just connect the dots or link them together. So as you see here from our outside radius value that we have, we just clicked on our output and we tied it into our radius argument. And that's what these wires do. They say, use this value to satisfy this argument. All right, so operation and function nodes, they allow us to do math and organize data without making extra nodes within the model itself. So for our example, we're going to use an operation node to divide the degrees in a circle by the number of holes we need. We'll take advantage of the node for degrees in circle and use that as our subject for the operation node and our limit in the function node. So the operation node is dividing the degrees in the circle by the number of anchor bolts, and that's going to give us our spacing. And we're going to use that downstream to basically set our coordinate systems for the arrangement of that bolt pattern. And in our example, the function we're going to use is going to be a series function. And we're going to use that to determine the angle, the rotation angle of each one of those bolts relative to our base plate. So we're going to take the output of our operation node, and we're going to use that as the start value for our function. So basically, we've identified we have a 30-degree rotation for each one of these bolts relative to the 24-inch diameter that we're using. And we're going to use that and connect it up to our start. And then our limit is going to be our degrees in a circle. So we're going every 30 degrees up to 360. So the function output is going to be 30, 60, 90, 120, 150, all the way up to 360. So what that does is it gives us a list of rotations that we need to use. And ultimately, that is going to feed into a coordinate system that is going to rotate at those rotation angles. So next, we're going to create the smaller circles on the inside of the base plate for the conduits. Again, we're going to follow a similar method of placement. So we're going to use that same technique of by center radius, and then we're just going to use a couple other coordinate systems relative to our base CS to place those. So the coordinate system technique we're going to use is just by Cartesian coordinates. You can also use by universal transform, but what that allows you to do is say, all right, relative to my base CS, that'll be my coordinate system argument. You know, X, Y, and Z difference. What do I want to do? So for us, we're just going to move in our Y direction, which is up and down this way. So we're going to go to the right and to the left. And we're just going to go at an offset of, I believe I keyed in here, 2/12. So 2 inches to the left and then 2 inches to the right. So try to keep in mind, too, the orientation of your base CS, as well as how you would ultimately want this cell to come in. So knowing that when I place this cell, I want this to be perpendicular to my direction of traffic, I use that assumption to organize and align all of my various objects. So everything is going to be built into the Y direction of my GC model. All right, so here's where we're going to see the, excuse me, here's where we're going to see those rotation angles come into play with our coordinate system. So we're going to create coordinate systems for the anchor bolt holes. So what we're going to do is use a technique for the coordinate system. It's called by origin rotation about coordinate system. And what we're going to do is basically say, all right, create a coordinate system that is relative to our base coordinate system. And then from that, rotate around an axis. So that's ultimately all the arguments here that we're trying to facilitate. Now, the nice thing about nodes is, depending on the node type, you're able to facilitate a single value or a series of values. So for us, we're able to take our function output, so that's the list of 30, 60, 90, up to 360, all of those rotation angles, and use those as the argument into the rotation angle field here. So basically what that's going to do is rotate every 30 degrees and place a coordinate system for us at each one of those intervals. And that's going to be relative to our z-axis. So the z-axis going up here. Now, once we have those, that's great because it gives us the rotations, but it doesn't put us at the location of the bolt circle. So what we need to do then is place a coordinate system relative to those rotated coordinate systems and just offset them in our y direction at whatever the radius of our bolt circle is. And that's what then places us at that correct location within our base plate. Right, so once we have all of the coordinate systems set, the circles built, all we have to do is come in and extrude them. So with our solid node, we have a bunch of different techniques we can use. The one we're going to show here is just going to be offset from closed curve. And what that's going to allow you to do is find any circle in here or any closed curve object. It could be a polygon, it could be a cone, it could be a circle. It's a whole host of nodes that you can facilitate this with. But basically identify that object and then tell it go above or below for your extrusion. So what we did is we used our value node for the thickness of our base plate, and we wired that into our height above. And then for our height below, we just used 0. We only wanted to extrude in one direction. For the next solid we were using, what we needed to do was use some Boolean operations. So we're going to have all of these small extrude circles as well as the overall base plate circle that are extruded. Now, when you look at it, it's basically all one object. They're all superimposed on each other. So we need to be able to subtract those from each other to give the holes so that we can see it. And what the Boolean operation allows you to do is specify, what object is to remain, and then what object needs to get subtracted out. So what we did is we just linked a bunch of these up together to subtract out the 3 or 4 different holes that we needed to have. And basically the way this works is it's saying, all right, I want to take my solid to stay, solid 0, and I want to subtract out solid 1, and the operation is going to be the difference. So once I have those nodes wired in here, you get a resulting solid that has that subtracted information out. And then that subtracted information solid is going to serve as the input for the next subtraction. So you're just going to kind of work your way down until you have all of the objects subtracted out. And the final product is going to look like this. So basically we had 1, 2, 3, 4 final merges. Basically we just took out the holes from the left and right, the center, and then all of the solids generated from that rotation coordinate system. And our final base plate here is what is shown. These things that are kind of grayed out, basically there's techniques that, so for example, the solid technique where you're merging, the inputs into those get grayed out and they get turned off in your visual display. You're only seeing what is turned on. You could turn these back on. You would just see basically objects superimposed on each other. But basically as they're not needed anymore or they facilitate something downstream, they turn themselves off for the visibility to make it make sense. You'll see that in some nodes, solids specifically, they do that a lot just to keep it clean. All right, some of the more advanced topics we'll jump into now. So we've got 2 big ones we'll highlight on, the generative node types and then node scripting. So GCP files are the extension that these get saved as. They're the generative node type. But basically what this allows you to do is take a very repetitive or common element that you would be building and save that as a custom node within your environment. So for the one that we did for the cantilever sign structure, we built the U-bolt assembly. So basically the brackets that hang on the arm that hold up the support for the sign. We wanted to make that something where I didn't have to build that 100 times because the GC model of itself is kind of complex, or it's very large. Like it's an easy model to build, but there's a lot of nodes involved with it. So we want to consolidate 50 nodes down to 1 node and just have that be something that we can select and use on this project as well as potentially on other projects. So what this allows you to do is take stuff, basically compartmentalize all the different pieces of a sign structure and make them more organized and easier to use on the current project as well as future projects. All right, so node scripting. Basically, you can, if you don't have something out of the box that works, you can essentially script GC to do whatever you want it to do. But it does require an understanding of the language it uses. And the language it uses is GC script. It's a C-style programming language, and it's unique to GC. Let's see, it's really powerful when you get into some more intricate or detailed modeling where it allows you to consolidate a lot of things. So for example, like the noise walls, I was able to take a script that had maybe 500 nodes and consolidate that down to half by utilizing a GC script that I could run for the different iterations or the different segments of the noise wall. So it's really powerful when you have an organized script. It allows you to consolidate stuff a lot more. So here's the U-bolt assembly I was just talking about. Basically, the screenshot here on the left, these are all the nodes wired together to build this U-bolt assembly. Now, this looks more complex than what it really is. It's basically just a bunch of points and extrusions that are put together. But I don't want to have to build this entire thing every time I build a GC model. I want to be able to just say, all right, I want to build a U-bolt and I want to modify a couple parameters and be done with it. So you can use this generative node type tool to essentially pick your inputs, and that'll list all the nodes that are hooked into it. And then from that, you can store it in your GC environment. And what that does is it creates a custom node here on your node panel, which looks like this. I called it U-bolt assembly. And when I select that node and drag it in, this is the result that I get. So I just have to identify the coordinate system that I want it to be relative to. I need to specify the pipe diameter, which will cause these U-bolts to flex and get larger or smaller. And I want to specify a flange thickness offset, so the flange relative to how deep it is. And then the diameter of the actual U-bolt itself. So is it 3/8, 5/8, whatever. Once I facilitate those arguments, I will see this object show up. So filling out 4 is a lot easier than building a node with like 25 or 30 different, or the GC model with 25 or 30 different nodes all linked together. So generative node types are very powerful as you start to get more familiar and identify a lot of common or recurring objects that you want to use across multiple projects. Here we're going to see some examples of the noise wall as well as rail ties and their custom scripts. I don't want to get into this too much, but basically it's a really powerful tool in the sense of if you understand how the node and arguments work, you can basically say, all right, I want to build a bunch of these different, I want to use a bunch of these different techniques or commands within this node and then facilitate their arguments within the script. And that's ultimately what this is doing. You're placing points, you're creating objects, and then you're outputting a final object. So it's consolidating a bunch of nodes that may be out of the box into a single node where it's doing a lot more things inside of it. So we have a noise wall. That's a good example of that and where you can leverage it. The rail ties is another good example of how you can place rail ties relative to cant or super elevation on your rails. I'm not going to get into the specifics of how the script works, but just know that it is possible, and there's some content out on YouTube and the Learn server that kind of goes into more detail on how the actual language is built. These are just a blow up. So this is the noise wall script. Basically what this is doing is it's going through and finding, linked to a spreadsheet, my range of coordinate systems. And then at each one of these coordinate systems, I'm going to be building points. And once those points are built and it's looping through that range, it's going to place points and then collect and build a polygon from it. So basically all this is doing is placing points relative to a coordinate system within a series of coordinate systems and then outputting a solid that's extruded that looks like my wall panel shape. This is a snapshot of the top of rail. Basically what it's doing is it's looking through a loop, identifying the count of how many coordinate systems I have in the range, and then it's orientating itself to draw lines and setting directions so that I get the appropriate tilt with the super elevation that goes on to place the coordinate system. And then I just place a cell relative to that coordinate system as it goes through. So here's some more examples of how you can leverage GC. It can be really powerful within your D&U cell creation, especially if you have clients that allow you to modify their standards. So PennDOT, for example, there's a lot of modifications that can occur within their top units. So GC allows you to kind of create those pretty quickly as far as like the bottoms and tops once you have the objects built. It allows you to quickly reference in, reference out, and then export it. And then from that, you can add in your symbologies to use for the DNU stuff. So that's a good example. Yeah, this is just building the bottom cell. And then we also have 3D stationing. So it doesn't have to be stationing per se. It could be unique callouts or text that you want to see in 3D. It can be helpful if you want to see like an odd spacing, or maybe not a interval spacing, but like a random call out of a station. You can hook this up to Excel and have text display at whatever increment you want to do relative to the coordinate systems that you're placing along that object. So think of stationing or just 3D text at locations relative to geometry. It can be powerful that way. That's just an example of the graph for that. So key things to know about this is there's a lot of similarities in all of the different consumption setup. You're going to have a range box that's finding a piece of your model, and you're going to be finding it based on like a level symbology. Once you have that, you're going to be decorating that object with coordinate systems of some type, whether it's a spacing interval, whether you're hooking it up to Excel to specify spacing, or you're just keying in a constant spacing value, or if you're using functions and operations to feed into it. Ultimately, what you're doing is you're decorating an object with coordinate systems and then placing elements relative to those coordinate systems. Same thing with the Excel range, reference attach, coordinate systems. All of these are very common nodes that you're going to see yourself using a lot as you start building GC models. We kind of touched on this. The workflow and the GC model creation. You'll start to see a lot of similarities in the differences in the different models you'll build, but they all kind of get assembled the same way. All right, so Steve Willoughby sent this to me just so I could have something to touch on the OpenBridge stuff. But basically, OpenBridge allows you to link directly to a GCP file. So this comes in really handy when you don't have. Let me make sure I play this. Bear with me 1 second. Gotta try to. There we go. So I'm just gonna let that play in the background. But basically what this is it's a GC model that was built that has a bunch of different variables that are controlling different pieces of that custom abutment. And ultimately what we're doing with this is we're saying, all right, I want to place that custom abutment in OpenBridge, but I want to be able to go through and modify the parameters of that GC model so that they're reflected in the OpenBridge model. So basically you're building your abutment, you're generating a GCP, and then you're importing that GCP into OpenBridge. And what that's going to allow you to do then is basically access generative components through OpenBridge so that you can make your modifications to it and have something that's custom that may not be able to be facilitated by a traditional cell that you would build as a functional component in here for OpenBridge. So he's just showing or demonstrating the workflow here on how to place that object. And then he's going to show how you can tie into that GCP and modify the variables of the GCP to have it reflective in your bridge model. So here he just placed it. Now he's going into the generative components workflow. And then from here, he's going to open up the variables on it. So here's our graph. He's going to double click on the final output here, and this is going to show all of the variables that are going into building that cell. So it's got the skew angle, it's got cap widths, left, right widths, all of that stuff. And he's just going to modify the variables within the GC workflow, and we're going to see it update within OpenBridge. So that's really what he's just demonstrating here. I know a few agencies have been utilizing this. I know PennDOT has. I know there's a couple other out there too. I think maybe Iowa DOT also use this, but GC can be very powerful in the sense where if you have something that's like a one-off or something that's really unique, it allows you a little bit more flexibility in some of the traditional 3D modeling methods for generating substructure elements. So that's basically what he's demonstrating here. All right, and then here's a couple examples of the noise walls and the sign structures that we built. So this is for the Betsy Ross Interchange project in Philadelphia. They have a noise wall on top of a viaduct ramp that's connecting the Betsy Ross Bridge to I-95. So that's a couple screenshots of it. For the noise wall, we got really detailed. We put all the anchor bolts and the anchor assemblies in with it. We had some unique posts that we had to draw in. So we built those with GC as well. Then basically we just did a linear pattern or linear array of saying, every X feet place this type of post. And then we used Excel to control the ranges. And then from that, we specified whether it was a type 1, type 2, what have you, and basically build all that stuff there. Here's a sign structure, a little more detailed one that we did for the Betsy Ross project as well. Again, that's got all of the assemblies on it, the U-bolts. We got the individual bolts in there, the end caps, the WT, W sections, the extrusions. So all of it. It can get really detailed really quickly. So there's a couple more screenshots. We got the anchors in there as well. And that's basically it. I see we're almost at the top of the hour. Didn't get to leave as much time as I wanted to for questions, but I don't know if this QR code still works, but I can copy and paste this link, and this link has all of the DGNs and GC models for the digital delivery workshop that we built so that you guys can open it up and explore. Let me see if it still works. It does. I'll copy and paste this and put it in the chat. That way you guys can access it. But basically what you'll see is all of the different sign structures. And then I've got the demo in here for the base plate as well. So with that, if there's any questions, feel free. That's basically it.